Okay, so we shall be talking about types of quantum numbers. And the types of quantum numbers we have are four. You have the principal quantum number, you have the azimuthal or subsidiary quantum number, you have the magnetic quantum number, and you have the spin quantum number. And let's talk about that. The principal quantum number is designated by small letter n. And this principal quantum number can also be represented by values such as capital K, L, N, O, P, so on and so forth. And what's the work of this principal quantum number n? The work of this principal quantum number is to tell us the energy level or the shell in which a particular electron can be located in. Because in the atomic structure, these electrons are not just everywhere, but they can be located in certain energy levels. And just as quantum chemistry says that energy levels are quantized according to quantum chemistry. You know, the energy values you cannot find an electron between the energy level 1.1, 1.2, 1.3. That is why this energy comes in discrete parts. And as such, we are saying that this principal quantum number describes the energy level in which this particular electron is actually located in. And it can take values ranging from 1, 2, 3, 4, 5, which corresponds to these alphabets you have in K, L, N, O, P, so on and so forth. So we are saying that N can take values for positivity such as 1, 2, 3, 4, 5, 6, so on and so on. Forth, which the 1 corresponds to K, 2 corresponds to L, 3 corresponds to N, 4 corresponds to N, 5 corresponds to O, 6 corresponds to P, so on and so forth. So, how do we explain these about energy levels? Now, let me give you an instance of the lithium atom, the electronic configuration, a simple model of electronic configuration of the lithium atom. So, for instance, you have lithium. Lithium has 3 electrons. And in a simple structure is that you have this here, you have the core shell in which lithium has 2 electrons, and in the atom's shell or energy level, lithium has 1 valence electron. And the electronic configuration is giving us 1s2 and 2s1. Now, why you write 1 and 2 is that you're talking about the energy levels. For instance, what you mean by 1s2, you see that 1 is representing the first energy level. So, and this is the first energy level, and it's equal to what? 1 or what? K. And the second one is N is equal to 2 or what? L. This is the second energy level, this is the first energy level, the second energy level. You come from inside to the atom's shell. So that is the whole basic work of this principal quantum number. It's just as if you're trying to locate your friend. Let's say Samuel is your friend and you're trying to locate him. Where is he? So if you're going to ask based on countries, you say that Samuel is in your country, Nigeria. Right? This is the whole general theory on a broader note, okay? It's there, okay? So it's Nigeria. So this is talking about the energy levels that are in the atom, okay? All right. So let's take a look at the second quantum number. The second quantum number is the subsidiary. The subsidiary or the azimuthal quantum number. Now, the azimuthal or subsidiary quantum number is designated by small letter or lowercase l. And what is its work? Basically, the azimuthal quantum number talks about the particular orbitals in which you can locate this electron in an energy level, right? So we are saying that Electrons are actually in energy levels. They're not just random anywhere in energy level, but they are being housed by sub-energy levels known as orbitals. Of course, an orbital is a region in space where the probability of locating an electron is greatest or highest. So these electrons are in energy level, but they're not just random anywhere. They're in the energy level and they're still in sub-energy levels known as what? Orbitals. And these orbitals are S, P, D, F, so on and so forth. Now, the work of this subsidiary quantum number or assumptive quantum is to tell you which particular orbital inside an energy level in an atom can you locate this electron that you are talking about. For instance, let's look at the electronic configuration of lithium here on the board here. If you're talking about the first shell, the electron in the first shell, you ask them, this electron is the first shell, but in what orbital, what orbital is it? Is the first energy level, but what orbital? So according to this, the electrons are in the what? S what orbital. You cannot see P here because the first orbital has a maximum of just one what orbital, which is what? The S orbital. If you're talking about this second orbital, the second energy level has two orbitals, S and what? P. So this electron you're talking about is in which of the orbital? Is it in S orbital or in what? In P orbital? P orbital. And definitely in this case, you realize that it is in the what? The S orbital. So this subsidiary quantum number tells you the particular orbital. It is this that is telling you that this particular thing should be S. This orbital should be S. This orbital should be what? S. And as such, it also takes values ranging from 0, 1, 2, 3, 4, so on and so forth. Whereas, when the subsidiary quantum number takes the value of 0, it's talking about the S orbital. When it takes value 1, it's talking about the P orbital. When it takes value 2, it's talking about the D orbital. When it takes value 3, it's talking about the F orbital. When it takes value 4, it's talking about the G, so on and so forth. These are for very extremely large atoms. Extremely large atoms, but it's beyond the scope of today's context. Now, that is the whole idea about this. You can liken this to the sub orbitals to like a hotel. And the hotel has room number 1, room number 2, room number 3, room number 4, room number 5. Right? That's it. So these are particular rooms in the hotel. So the hotel stands as your entire energy level. So this energy level has sub rooms. The hotel has now rooms. It has suites in it. So basically this room 0, room 1, room 2, room 3, room 4. So it's telling you that this room 0 corresponds to the S orbital, P, D, F, G, as the case may be. Now, let's also look at the third quantum number. The third quantum number is the magnetic quantum number. It also has its own function. The magnetic quantum number, represented by small m or M subscript L. This magnetic quantum number talks about the degenerate orbitals. And what are degenerate orbitals? Degenerate orbitals are subatomic orbitals that have the same energy level. Now, remember, we had told you before that these degenerate orbitals are suborbitals that have the same energy level. The orbitals that have these degenerate orbitals includes the p orbital, the diffuse orbital, the fundamental orbital. The p orbital has suborbitals such as px, py, and z. But all of them have the same energy level. That means that if this is the second energy level, then it will be 2px, 2py, and 2pz. Is that good? So, now this magnetic quantum number talks about the subatomic orbitals, the degenerate orbitals that you have here. It's describing. In this electron you're talking about, is it inside any of these degenerate orbitals? If it is it px, py, or p what? Pz. Now let me give you a very good example of what I'm talking about here using the electronic configuration of neon. Now, if you look at neon here, neon has how many electrons? 10 electrons. And the electronic configuration goes thus. You have 1s2, you have 2s2, and you have 2p6. Now, in this 2p6, it means that in the p orbital, you have 6 what? Electrons. So, in these 6 electrons, we say p orbital has 0 orbitals as what? Px, py, and p what? Z. This is 2, 2, 2. Then there is the same energy level. So, now, where is a particular electron you're talking about? Where is it? Okay? So, these are sub-orbitals in this particular orbital, but they have the same what energy level. So, in this, you're supposed to have 2px2, 2py2, 2pz2. So, is it the electron that's in px, py, or pz that you're talking about? So, the quantum number that will describe precisely the particular subatomic orbital you're talking about is the magnetic quantum number. It tells you the subatomic orbital in which you are talking about. Now, let's look at the fourth quantum number, which is the spin quantum number. And the spin quantum number is designated by ms code s. Now, the spin quantum number talks about the spin of these electrons. Now, because we understand that on light charges they tend to attract, positive and negative tend to attract. However, light charges such as positive will tend to repel and negative will tend to repel. And we know that electrons are actually negatively charged. And based on Pauli's exclusive principle, when these two electrons enter in this degenerate orbital, px, when they are two there, one of them will have to spin up, the other one will have to spin down in order to minimize repulsion and be stable in this particular orbital. And as such, this spin quantum number tells you that this electron could either be spinning up or could either be spinning down, and it is designated with values such as negative half and positive half. And this explains why, according to Pauli's exclusive principle, no single electron in an atom can have all the same values of the 4 principal quantum numbers. It's impossible. Even if they are in the same orbital, they will not have all. There will be a change at the spin quantum because one will spin up and the other one will spin down. So it is practically impossible for you to have that. Yes, it's a mathematical approach that helps us to understand the behaviors of these electrons inside an atom. Okay. Now, it's very important. It's very, very important for you to understand these basic ideas about these quantum numbers. And that's it for today. If you have any question, don't hesitate to ask us in the comment section there, and I'll be able to answer you. Or you can send me any question or any problem you have at this email, apologis9@gmail.com, and you will have your reply suitably as you can. Thank you.